Okay, we're going to go over Lecture 1 today, and actually I'm defining Lecture 1 by the slides, not because she completed this lecture in the second lecture as well. So we're just going to talk about general mass transfer and diffusion and fluxes. And we won't go over the lecture objectives, we'll just talk about what we did. This was an example that she gave showing the blood flowing through a capillary here. Here's the capillary. And you've got wastes coming from the tissue and glucose coming from the capillary out to the tissue. And it is passing in from the capillary into the tissue and through the tissue by diffusion. And the question, the problem statement was, what is the concentration of the waste as a function of distance from the capillary, or the same for the glucose? And what you see here, these equations here, are an example of things that you will be able to do later in the semester.
Okay, so this isn't a, I'm teaching you this today, please memorize. This is a sort of overview of these are the kinds of problems you'll be seeing throughout the entire semester.
Exactly, and to give you an idea of where you will be in a little while, where you'll be able to do these kinds of things.
So don't worry about memorizing this right this very moment.
No, not at all. Whoops. I don't know what happened here. Okay. And here's another example where you have a kidney patient here who is on hemodialysis, and they're taking his blood out and passing it into the hemodialyzer. And so the blood is traveling through here, and this is the fluid that they're passing through on the other side of this membrane here. And so you've got things passing from one side to the other through this membrane, and then the blood is returned back to the patient. And in this example, the problem would be to determine how much of the toxins that were in the blood are being removed. And once again, this is just an example of something that you will be able to do later in the semester, so you can be amazed at where you will be soon.
So again, like, not worry about this right now, but
no, not at all.
But it's supposed to look like something you don't know yet.
Right. It's something to look forward to. And then here's a third example where we have a biofilm of some organism here. And there are organisms in this biofilm that can treat wastewater. And so the wastewater, whatever is the material in the wastewater that the organism is going to react with, needs to diffuse through the biofilm so that it can react and be treated. So this is just another example of the same thing, of the equations that you can marvel over now that you will be able to do at some point in time.
So right now, as we're going through this intro, what is it we're supposed to be getting? Is it like, what is mass transfer?
Yes. Just that things are diffusing through phases, through regions. So that's basically all there is to that.
So mass transfer is stuff like mass that is moving and being diffused through membranes or fluids or solutions.
Or gases or solids. Yes, exactly.
Okay, that's literally, that's it.
That's it. That's all you need to know for now. But as you can see, there's some interesting math to it that we will be tending to this semester.
But not now.
Not right now. Okay, so I'm going to pass that up and just head on. Now, actually, how does this happen? Well, here we're seeing different phases. We are seeing solids, gases, and liquids. Let's start with the gas. In the gas phase, in all phases, you have this random Brownian motion of molecules.
Mm-hmm.
And so she's been able to show it very nicely here for the gas. It's random. There's no purpose to it. And it's happening not only in the gas, it's also happening in the liquid phase, and it's even happening in the solid phase. But the liquid phase, it's happening less than in the gas, and the solid even less. And the whole point here, if we look at this part, which is the liquid, we see these little circles are some species other than the solvent species. And it's pretty homogeneous here. It's well mixed. In this second one, where it's inhomogeneous, we see these circles, which are component A, which are in the solvent we'll call B. It's not well mixed. And so when these molecules do their random movement, you'll have a lot of movement upward from the high concentration area and just a little movement downward from the low concentration area. And so the net result of this is that you will have material that moves from the bottom up to the top, from the high concentration to the low concentration. And that's what diffusion is. It's just a result of this random Brownian motion.
So like a non-fancy way to talk about it would be if you've got like a tub of water and then you put paint on one side, it eventually all the water becomes evenly colored. Right? So we're moving from the inhomogeneous to the homogeneous case.
Yes, usually.
Usually.
Assuming, there's not any gravitational settling or anything. We're ignoring that right now. You can even have that in the solid phase. There is some random motion in the solid phase, but not nearly as much as there was in the liquid phase. So there can be some of this movement in the solid phase as well.
So in a biomedical engineering setting, usually when we do mass transfer, is it going to be with liquid or gas?
Usually liquid, but there could be a gas phase. There could be a solid phase. But I would say usually we're talking about liquids.
Okay. And then we'll get to fluid stuff later in the semester also and go deeper into that.
Right. Speaking of fluids, and I think you were mentioning like fluid flow, there are two different ways that mass can be moved. One of them is diffusion. So here we have a stagnant vat of let's say this is water, and these white circles are sugar molecules, and they're, in this case, maybe we dropped some sugar to the bottom of the vat of water, and the sugar is now diffusing.
So it's like my cup of coffee in the morning.
Exactly, without you stirring it.
Yep. So I just drop the sugar in, and it's still kind of slowly pervading the coffee.
Right. And then the other mode is convection, and this is where you're putting your spoon in the coffee and stirring it because you want to hurry this process up.
Right, because I have to get to class.
Right. So convection is generally much faster than diffusion. Right now we're focusing on diffusion. We'll talk about convection a little bit later, a few lectures from now. When we talk about diffusion, we need to talk about concentrations because diffusion, the driving force of diffusion is concentration, a higher concentration versus a lower concentration. So there are several ways that we can define concentration. One of them is with the mass concentration, which it's the density of the species A. A is what is diffusing. It's just mass per volume. If we add everything up for all the species, we get the total density, which is the total mass concentration. We can also use the mass fraction, which is just the mass of that species over the total mass. And here you might not be able to see that very well, but if you add up all the mass fractions, of course that equals to 1. Then the molar concentration here, molar concentration of A, is just moles per unit volume. If it's an ideal gas, then you can use the ideal gas law, and it is just the partial pressure of that species over RT. And then, of course, the total molar concentration for all the species is the same thing. Here we go. Total number of moles per volume. And if it's an ideal gas, how did that happen? If it's an ideal gas, then we just use the total pressure over RT.
So, there's a lot of formulas on the slide, and which ones are important to memorize or be able to derive? I mean, at this point where we're just starting to talk about mass transfer.
Actually, I think you should already be familiar with most of these. The mass concentration and the mass fraction, of course, I think you should have seen those several times before. The molar concentration and for a given species, and for the total, you should have already seen. So you should feel comfortable with those.
Okay, and in terms of the symbols being used here, so for mass concentration, I see the rho. For mass fraction, I see the omega. For molecular concentration, I see C.
Mm-hmm.
Are these symbols things that we should already be familiar with?
Yes. This is using the same notation as you have already seen in 2210.
Cool. Good to know.
Okay. And of course, mole fraction is just the number of moles over the total number of moles for
Makes
both
sense.
liquids and solids, and also for gases. It's also the concentration of that species over the total concentration. So it's the same. Both of those are the same for liquids and solids, as well as for gases. It's not working here. As well as for gases. Also, for gases, using the ideal gas law, the mole fraction is the partial pressure over the total pressure.
Okay, so these are all just terminology. Here are some ideas, some representations
Yes.
of different ways you might talk about these kinds of situations.
Yes, and you should be familiar with these.
Cool.
These shouldn't be new to you. Okay, now velocity, this is a little tricky. And we're not going to do a whole lot with it at this point, but just to be aware. So we've got the mass average velocity, which is basically what we're going to do is we're going to take each component. So like over here, I've got lots of different things in my solution. Some of them are diffusing up and some of them are diffusing down. And so they each have a velocity. And I'm going to take the mass concentration here of each species times its velocity, and then divide by that total, which turns out to be the total density here. Okay, and that gives me the mass average velocity. The molar average velocity is basically the same thing, only we're going to use the molar concentration for each species.
And why would you use one or the other? How do you choose what to use in a particular situation?
I guess it just depends upon what's most convenient for the problem at hand. If you take, for a particular species, if you take its velocity and subtract the mass average velocity, you get the diffusion velocity. So that is how fast it's diffusing through the region relative to how fast the region is moving. And here is the same thing, only on a molar basis.
Okay, so it's like you've got the mass average velocity, which is sort of like all of the molecules are on a moving walkway, like in the airport, sort of.
Oh yeah, that's a good way to think of it.
And then the diffusion velocity is, if we take away the moving walkway, just how are you moving relative to everybody else on the conveyor
Well, it
belt?
would be, yeah, you'd be walking on the conveyor belt.
Mhm.
Some people are walking forward, some people are walking backwards.
Okay, and the reason we separate those two is, I'm guessing here, but because we'll often have situations where it's like all the blood is going through the vein, all the blood is moving, but some stuff is moving through the bloodstream faster, and like at the same time the blood is moving, we have this drug moving through the bloodstream too.
Yes, yes. Yeah, so we've got different things happening, and they're additive.
Okay, so far so
Okay.
good.
Yeah. So here's an example of that, and I don't want to get into too much detail because it's not something that you'll be responsible for, but just need to be aware of. So in this case, we have liquid A down here in an open tube with gas B here. So if I say, maybe this is benzene,
Okay,
which is volatile and can evaporate, and I've got nitrogen gas over it in an open tube. And let's see, on this side, she is showing, for example, in the pink, she's showing the concentration with Z, which is elevation, and you can see the concentration here is high, and then it asymptotically approaches zero as we go up in elevation. And she's just giving a few values just for example. We're going to a position where the mass fraction, I can't draw on that for some reason, where the mass fraction is 1/6, so that's this line here. And she says at this point, the molar average velocity is 12, which means that on average, all the material is moving up. And the diffusion velocity for component A, which I called benzene, is 3. So the benzene, or component A, is moving upward.
so I'm not sure I see the difference between the mass average and the diffusion in this case.
So it's actually the molar average.
Mm-hmm.
So on average, this material, the material in the tube, gas B and what's now gas A,
Everything
is moving upward. So it's moving out of the tube. It's going to spill out of the tube.
Oh, okay. So
Okay.
it's an open tube, and the gas is also coming up, as well as the nitrogen gas is also coming up, and the benzene is evaporating and coming up.
Everything's coming up. And the benzene, well, component A, is actually moving faster.
Okay, so they're catching up to the nitrogen, sort of spreading through it as
It's-
they both.
Yeah, they're both moving, but the benzene is moving faster.
Got it. Okay, thank you.
It's got farther to go, though. And the component B, here, we're not going to go through the calculations, but she did calculate the velocity of component B is 11.4. So component B, which started out as the gas here,
Mm-hmm.
is also moving up and out of the tube.
Okay.
Okay. Relative to how fast the fluid, the gas is flowing out of the tube, it's a negative. So its relative velocity is,
Slower.
it's slower. Yes, thank you. It's slower. But it's still positive. It's still moving. And if you imagine after some period of time, the only gas that would be left inside here would be component A, and very little of component B. Okay, so anyway, this is just an example just to show you
And this
the
is like,
velocities.
and this is like showing how we talk about it, how we describe it. We don't have any way of actually, how did you get to these numbers quite
Right.
yet?
No, we're not going to talk about that right now.
Okay,
It just so that you know.
got it.
Definition of a flux. A flux is anything per unit area. So in this case, it's a mass, for example, a mass flow rate per unit area. Okay, or a molar flow rate per unit area. How many moles per second per square centimeter, for example?
And so this is just the same concept of flux as in, intro physics class. We might have talked about it as, I'm an electrical engineer, so like charge passing through, right? What is the current? Or the charge passing through the surface?
Right. So
But here you've got like actual things.
Right. And so flux is just anything per unit area. Now we're getting into Fick's first law. So how do we quantify what's happening in terms of the diffusion? So here's the diffusion flux. We're just going to look at it in the z direction right now. It is proportional to the gradient in the concentration. So the bigger the gradient, the faster it's going to diffuse.
Okay, and I see that the gradient here is defined as the derivative of the concentration.
Right. Also, this negative sign here, this negative sign comes about because it's traveling in the direction of decreasing concentration.
Okay.
And so if it's traveling in the positive direction, that means that this gradient here is negative.
And is that a convention that would hold true for, anytime you set up an equation related to diffusion, a higher concentration is always in a positive direction?
It's always traveling from a high concentration to a low concentration.
Okay.
So we need that negative sign there. And then finally, we need some kind of proportionality constant, and that's the diffusivity.
And I see that's down at the bottom of the side.
Here, right here, the mass diffusivity or diffusion coefficient.
Okay.
And this is for component A diffusing through component B, and that's what that means.
And that's something you would find out experimentally, typically?
Yes, but we have empirical correlations that we can use in order to estimate what that diffusion is.
Okay.
What that diffusivity is. If you're looking in 3 dimensions, you can use this equation where this del operator, whoops, I drew it upside down. A del operator is just partial with respect to x plus partial with respect to y plus partial with respect to z. That's all that means.
Okay. So it's a shorthand for, oh look, we've got differentials in multiple dimensions.
Right. So this would be the partial of CA with respect to x plus the partial of CA with respect to y plus the partial of CA with respect to z. That's all that means.
Okay.
And then, of course, this one that we've been looking at is just the one in the z direction. All right. So that's Fick's first law. This one, right here. This is a big one, so memorize that one.
Okay. So that is something that you should study for quiz 1.
Absolutely. Okay, and this is just some examples of the different, like this is Fick's first law in terms of, so up here we had it in terms of concentration, C sub A, and if you divide by the total concentration, then you can make it in terms of the mole fraction. So
okay.
That's the only thing that happened there.
So it's just, these are just different representations.
Right. The capital J means molar flux. The small j means mass flux. And here we've divided by the total mass concentration, or the density, which means that we're using mass fractions here.
Okay, and I'm noticing that seems to be a terminology consistent thing where the capital is molar and the lowercase is mass.
Right. Yes. And then that's J's. Now we're looking at N's, so capital N sub A is, once again, it's capital, so it's molar. It's the molar flux of A. But now, this is previously our molar flux was relative to something that was going along with the flow.
The conveyor belt thing.
Right. Now it's relative to somebody sitting at the side of the stream and watching it flow by.
Okay.
So we're going to add a term to account for that.
And I can see, in different setups why one might be more useful than the other. For instance, you want to see this drug diffusing through the bloodstream from the perspective of going along with the bloodstream versus, but we're sampling from this port here. So we care about it from the perspective of the port location.
Or a piece of tissue that's sitting there watching the blood go by.
Okay.
A lot of ways that you can think of it. Yeah.
And studying for the quiz-wise, are these all important to memorize, or is it just learn about fix?
Well, as Dr. Babincy said, in many biomedical applications, since we are multiplying by, here's the mass fraction, here's the mole fraction, and often that's very small, which means that we can neglect this portion. Neglect because it's going to be so small, which means that now this and this are basically the same.
Awesome.
Okay? I wouldn't say that's always true, that you can neglect it, but in many cases you can. And in this class, she has indicated that we will be doing that.
And that's a good life strategy in general. Whenever you can get rid of a term, make your life easier, do it. It's engineering. We approximate.
Right. Okay, here's an example from the homework, which I think I'm going to pass up because I'm sure she has the homework. The homework has already been done.
Right. Solutions are posted. Y'all did it already.
Right.
You're good.
So then she talked a little bit about convective mass transfer. And at this point, once again, it's just so that you're aware of it. So convective mass transfer is when a fluid is moving. So it's moving over a surface or between two, or over the surface between two phases, for example. In this case, you've got fluid that's flowing at a velocity of v infinity, and it hits this is a flat plate. It hits it, and the friction between the fluid and the flat plate cause it to slow down up next to the flat plate. Actually, the molecules right next to the flat plate are at the same speed of the flat plate, which in this case is 0. That's called the no-slip boundary condition. And so it makes the velocities look like this. So they're slowed down next to the flat plate, and then they increase up to v infinity. Here, we're looking at the concentrations. And in this case, the concentration, it's a little bit backwards. She's saying that the surface at the concentration is greater than the surface at I said it backwards again. The concentration at the surface is greater than the concentration at infinity. In this case, what we're seeing is the concentration at infinity is greater than the concentration at the surface. So it's a little bit backwards, but it's basically the same shape of equation. But you can see that the concentration does change with elevation away from the plate.
Because the plate is... I'm trying to envision like what kind of situation this would happen in.
It's diffusing to the plate or away from the plate, one way or the other. If this is the case, it's diffusing from the plate's surface to the fluid.
Okay, so like an example of something like this would be like if you have a tablet that you're passing water or some fluid over to dissolve it in the stream?
Yes, yes. Yeah.
So like melt in your mouth stuff, so you've got saliva going past your dissolving vitamin or whatever.
Yeah.
These are not the best examples.
We're not really going to be talking much about convection right now, but you could think of it this way, that if this fluid weren't flowing, then as the material diffused from the plate into the fluid, right up next to the plate, the concentration would become high.
Right, right.
But as it diffuses from the plate into the fluid is sweeping that away, and the concentration of the fluid next to the plate stays lower.
Okay, yeah, that makes sense.
Okay, so that's basically why you stir your coffee to dissolve the sugar. That's why it dissolves faster that way.
And so this is like situations like getting waste products out of tissues by flushing them in the bloodstream or lymphatic system.
Yeah. Okay, so anyway, that's just so that you're aware of it. We'll be covering convection later.
Okay, so this is also a don't worry about it for the first quiz thing.
Right. Now, we can define how much or at what rate mass is being convected away from or to the surface using this equation here. Here's our flux. This is the difference in concentration between the surface and the C infinity.
Okay,
far from the.
So I'm noticing this is a delta, not a del operator.
Right. And this Kc is our convective mass transfer coefficient. And what we will have, once again, empirical correlations that we can use to estimate that based upon what's going on with the fluid.
And the convective mass transfer coefficient is something that you would look up depending on what the materials are?
Yes, you can look it up, you can measure it, you can estimate it from these correlations that we'll be talking about.
So convective mass transfer, like a sort of goofy, informal way of talking about it, is how spready out is this stuff? Is this combination of stuff?
If the fluid is flowing, if there is a flowing fluid.
Okay.
All right, and I guess that's the end for this particular lecture. Lecture 1.
Lecture 1.